This is the last of 3 lectures on reactions in aqueous solution, and this lecture will be on oxidation-reduction reactions. An oxidation-reduction reaction, which is called redox for short, means that an electron has been transferred from one reactant to the other. Oxidation means that an atom or ion has lost an electron. Reduction means that an atom or ion has gained an electron. Wherever there's an oxidation occurring, there must also be a reduction occurring. One cannot occur without the other. The mnemonic, the memory device I've always used that helps me remember, is Leo says grr. So lose electrons means you've been oxidized. Gain electrons means you've been reduced. Now throughout all of this, remember that an electron has a negative charge. So if you gain an electron, your charge becomes more negative. Okay? If you lose an electron, your overall charge comes more positive or less negative. All right, so again, a redox reaction means a transfer of electrons has occurred. A very common one that you can see, for example, in the formation of salt, NaCl, from its constituent elements. So if you react sodium with chlorine to get sodium chloride, that's a redox reaction. Okay, the chlorine atom has picked up an electron to become the chloride ion. The nitrosodium metal has lost an electron or given one up. They become the sodium cation. It's a classic redox reaction. When we have the formation of ions, it's really easy to see that it's a redox reaction. However, there are several other reactions that are redox that are not entirely clear that electron transfer has happened. In those cases, we may have a partial transfer of an electron, such as making a covalent bond where the electrons are not shared equally. You can kind of think of that as partial transfer of an electron. So my point is, there are some chemical equations where you won't be able to tell just by glancing at them that it's a redox reaction. So for those types of reactions, we use what we call oxidation numbers. It's a number with a charge, a plus or minus charge, that we assign to every single atom in every single compound in a chemical reaction to see if an electron has been transferred. It's kind of tedious, but it works pretty much all the time. One thing I want you to keep in mind is that oxidation numbers are not real. They are not charges. Okay, so NaCl, the plus and minus sign you see here, those are truly charges. They mean this sodium has totally lost an electron, this chlorine has totally gained one. Oxidation numbers are what we call electron bookkeeping. It's kind of a game we play just to keep track of electron movement. All right, so here are the rules for assigning oxidation numbers. The first thing to remember is that the sum of all of the oxidation numbers of the atoms in a compound must be 0. So sodium chloride, for example, its overall charge is 0. So that means the oxidation numbers that you assign to each atom must also add up to be 0. So sodium, we know, has a charge and an oxidation number of +1. Chlorine has an oxidation number of -1. +1 minus 1 does in fact equal 0, so that's good. Elements in their standard elemental form have an oxidation number of 0. So again, using our formation of salt from its elements, I have to balance this. That doesn't look like a Cl. There we go. The oxidation numbers that would be assigned to the elements on their own are 0. All right? The oxidation number of an ion is the same as the charge of the ion. Going back to sodium chloride again, we know that the charges on these ions are +1 and -1, the oxidation numbers of ions are the same as the charge itself. Okay, couple more rules or just guidelines that'll help you. Fluorine, being the electron hog that is it is, the most electronegative atom in the periodic table, always has an oxidation number of -1. That is non-negotiable. Most of the other halogens usually have an oxidation number of -1 also, but they can change. So you'll usually see chlorine and bromine, for example, with an oxidation of -1, but you might also see chlorine +1, okay? So just keep that in mind. Oxygen has an oxidation number of -2 the vast majority of the time, probably 99% of the time, except when it's in a type of structure called a peroxide. So hydrogen peroxide, for example, looks like this. So a peroxide link is when you have two oxygen atoms single bonded to each other. In that case, the oxidation number of the oxygens is -1 instead of the typical -2. That's quite an exception, though. Hydrogen is almost always +1. So if you have something like HCl, it's +1. If something like CH4, you can assume each hydrogen has a +1 oxidation number. Okay, except if the hydrogen is bonded directly to a metal. For example, NaH, called sodium hydride, the sodium takes precedence. The sodium wants the +1 charge, which then forces the hydrogen to have a -1. So again, if hydrogens are bonded directly to a metal, that is the only time you'll see them with a -1 oxidation number instead of a +1. All right, so again, as I said earlier, oxidation and reduction must occur at the same time. You can't have one without the other. Let's look at our favorite reaction, the production of sodium chloride. And let's say that we didn't know it was a redox reaction and we were trying to figure it out. What you do then is you write the oxidation number for every single element involved in this entire reaction. So sodium is an element by itself, has an oxidation number of 0. Chlorine's an element in its standard state, happens to be diatomic, but that's its standard state, so it also has an oxidation number of 0. Sodium chloride is an ionic compound with charges. We know that the sodium ion is +1, the chloride ion is -1. You are now done assigning oxidation numbers, and so now in order to determine whether or not anything has been oxidized and reduced, you compare the element before and after the reaction. So sodium starts out with an oxidation number of 0, and sodium ends up with an oxidation number of +1. So what has happened to sodium? In order to go from 0 to +1, it has lost an electron. Remember, electrons have a negative charge, so in order to get positive, it's got to lose an electron. If it loses an electron, it's been oxidized. Okay, chlorine goes from an oxidation number of 0 to an oxidation number of -1. So it has gained an electron. Okay, and so it has been reduced. So this is in fact a redox reaction, and that's how you go about determining if reactions are. Let's get some practice assigning oxidation numbers to compounds that maybe aren't quite as obvious as the other ones. If you think you can give this a stab, try it on your own, pause the video, and then come back and compare your answers to me. Alright, so this is how I would approach each of these. Carbon dioxide. I always start with oxygen. So oxygen is almost always has an oxidation number of -2. Put the oxidation number of a single atom up above it rather than combining it if there are more than one. So, but keep in mind, since there are two oxygen, that the total charge for the oxygen is -4. Therefore, the oxidation number of carbon has to be +4 in order for this to be totally neutral. Okay, let's tackle the polyatomic ion of nitrate. The first thing to keep in mind is that the sum of the oxidation numbers of the nitrogen and oxygen atoms must add up to be -1. So keep that in mind. So again, I start with oxygen. I'm going to rewrite this over here. Oxygen, as usual, has a -2 oxidation number. There are 3 oxygens, however, so the total charge for oxygen, it's not a charge, excuse me, the total oxidation number that oxygen contributes is -6. Now, if this were a neutral compound, I would assign an oxidation number to nitrogen of +6. But since the overall charge is -1, I'm going to say nitrogen has an oxidation number of +5. And that keeps the overall charge of -1. All right. Iron 3 oxide is an easy one. That's an ionic compound. And with an ionic compound, the oxidation numbers are the same thing as the charges on the ions themselves. You can do the little reverse crisscross trick here if you want. And that tells us that this iron has a charge of -3. That means its oxidation number is also -3. And oxygen, as always, has a charge and oxidation number of -2. The last one, sulfur hexafluoride. I would start with fluorine. 100% of the time, fluorine has an oxidation number of -1. So if we assign fluorine -1, keep in mind there are 6 of them, which means the total oxidation number of fluorines combined is -6, which means the oxidation number of sulfur has to be +6. So hopefully you followed some of that. Let's go over a couple different types of reactions that are always redox reactions. Combustion is one. Redox reactions originally got their name before they were more carefully defined as a transfer of electrons. They were described as reactions that involved oxygen. And of course, combustion reactions have to have oxygen as one of the reactants. And so it was one of the original redox reactions. But if you were to go ahead and assign oxidation numbers to each of the atoms in a combustion reaction, you could prove to yourself that it is in fact a redox reaction. So this is how I would go about signing them. Hydrogen, remember, has an oxidation number of +1 unless it's bonded directly to a metal, which it's not here. And in order to keep this overall compound neutral, that means carbon has to have an oxidation number of -4 because there are 4 hydrogens. Okay. This is oxygen in its elemental form, so its oxidation number is 0. Moving over to the product side, as always, we assign an oxidation number of oxygen of -2. Since there are 2 of them, that means the overall oxidation number for oxygen is -4, which means the oxidation number for carbon has to be +4. Then moving on to water, as always, the oxidation number is -2, and that for hydrogen is +1. Now we can look at all of these and decide what has been oxidized and what has been reduced. So let's see, carbon has gone from an oxidation state of -4 to the product side. It has an oxidation state of +4. So oxygen has lost 8 electrons, which means it has been oxidized. So something has to have been reduced. Hydrogen has stayed the same. It's +1 on the reactant side, +1 on the product side. Let's look at oxygen. It's gone from an oxidation state of 0 to an oxidation state of -2. Okay? So oxygen has been reduced. It's gained 2 electrons, going from 0 to -2. And so we verify this is a redox reaction, and we have identified what's been oxidized and what's been reduced. A single replacement reaction is another type of reaction that is always a redox reaction. You identify single replacement reaction. It always has an individual element that is trying to kick out or trade places with an ion. So in this case, the copper metal neutral element is trying to swap places with the hydrogen ion. So we'll show what's been oxidized and what's been reduced in this reaction. It's pretty easy. Hydrogen gets assigned an oxidation number of +1, which means chlorine has to be -1. Copper on the reactant side is a neutral element, so its oxidation number is 0. On the product side, this is an ionic compound, which means the charges of the ions become the oxidation numbers. Chlorine's -1, as halogens always are in ionic compounds. That means copper has to have a charge and an oxidation number of +2. Hydrogen now is an element, neutral element. Its oxidation number is 0. What's been oxidized and what's been reduced? Well, let's see. Hydrogen, going from +1 to 0, has gained 1 electron. So it has been reduced. Hydrogen has been reduced. And copper has gone from 0 to +2. So it has lost 2 electrons. So copper has been oxidized. And metals in general like to be oxidized. I don't know if you remember this, but metals have very low ionization energies. They tend to become cations and give up electrons. So you will very often see that metals are oxidized and that nonmetals are reduced. Alrighty, so this is a typical type of question that I might ask you in a quiz or a test, and I'm just wondering what happened to my reaction arrows here. Let's see. There we go. Alright, so I might ask you, circle the ones that are redox reactions. How would you go about doing that? Well, you would have to assign oxidation numbers to every single atom on both sides of the reaction, then decide if something has changed its oxidation number from reactant side to product side. So I recommend that you pause the video, you try to do it on your own, and then you come back and check your answers. Alrighty, last slide of the video. Assigning oxidation numbers. If you look at reaction A, this one's a little tricky. Mercury's kind of weird. It makes this kind of double cation thing. So you might think that each mercury has a charge of +2. That's not the case. There are 2 mercuries, so each mercury has a charge of +1. And that is an ion, so its oxidation number is the same. The polyatomic ion hydroxide, we're going to start, well, there are no surprises here. We'll give oxygen an oxidation number of -2 as usual, hydrogen an oxidation number of +1, and that works out really well because that means the net charge of hydroxide is -1, which is what it should be. And let's see, the mercury here, this is an ionic compound, so its charges are the same as the oxidation number. Oxygen is -2, each mercury is +1. Oxygen is -2, hydrogen's +1. Now, have there been any changes at all? Mercury has stayed the same. Oxygen has stayed -2. And hydrogen has stayed +1. No changes in oxidation number. That is not a redox reaction. Alright, number 2. Assigning oxidation numbers. Each mercury is +1. Tin is +2, clearly. Mercury in its elemental state is 0. Tin over here is +4. It's a pretty easy one. So tin has been oxidized, has lost electrons, and mercury has been reduced. That is a redox reaction. C, mercury is +1, And in the product side, as an element, it's 0. So I can tell right away mercury has been reduced. Let's look and see what's been oxidized. Alrighty, so let's see. Looking at hydrosulfuric acid, the hydrogen has an oxidation number of +1, and the sulfur is -2. So let's look at hydrogen and sulfur on the product side. Hydrogen on the product side is also +1. It hasn't changed. So we still haven't found out what has been oxidized. Let's look at sulfur. Sulfur has gone from -2 oxidation state on the reactant side and -2 oxidation state on the product side. However, with sulfur, just to kind of remind you, is in the oxygen group, and those all tend to have a -2 charge. This is an ionic compound, mercury sulfide. So in that case, we can pretty confidently say that sulfur, being in group 6A, has an ionic charge of -2, which means the mercury in this ionic compound has a charge of +2. So look at this strange situation. We have 2 mercuries on the reactant side with oxidation numbers of +1. One of those mercuries goes on to be reduced, but strangely enough, the other mercury goes on to be oxidized. So as it turns out, this is called a disproportionation reaction, where the same element is both reduced and oxidized. So that's kind of a weird situation. But reaction C is in fact a redox reaction. So far reaction B and reaction C are redox. The last reaction, reaction D, I'm just going to kind of quietly assign redox oxidation numbers. I know that mercury, this weird mercury, has an oxidation number of +1. I'm going to save you some time and effort here by pointing out a little hint. Notice that chromate, CrO4, which is a polyatomic ion, stays intact, remains as the same polyatomic ion on the product side, which means I'm not even going to waste my time figuring out oxidation numbers of the atoms in the polyatomic ion, because I know whatever they are, they stay the same, and they are not going to be involved in a redox reaction if there is one. So then moving on, oxygen hydroxide is -2, hydrogen's +1. On the product side, oxygen is -2, each mercury is +1. I'm not seeing any changes, okay? So oxygen on the reactant side is -2. It stays -2 on the product side. Mercury is still +1. All we have left is hydrogen. Hydrogen on the reactant side is +1. It's also +1 on the product side. So there have been no changes in reaction D. It is not a redox reaction. That is it for this lecture, and also Chapter 4, Reactions in Aqueous Solution.